In Appendix 1, we shall discuss a RISC, which stands for Recognition by Indexing and Sequencing, in detail. RISC is a general-purpose, non-parametric method for classification of temporal vector sequences. RISC has two basic steps. The first one is called training, which simply is storing all samples from example sequences in data structure. And the second one is called testing, which includes two subtests discussed in next slide. The first sub-step of testing is called indexing. Indexing, in a nutshell, means retrieving of the nearest neighbors of input sample from the training sequences by performing k-nearest neighbor search algorithm. The second sub-step is called sequencing, which is the process of finding an optimal sequenced matching between input sequence and retrieved neighbors of that class. Here we want to discuss the training procedure. At first, the training data is sampled with high sampling frequency. Next, the training samples are put in a KD3 data structure along with class identifier and timing information. In the diagram, you can see a sample of KD3 data structure. The samples stored are represented by the small spheres. Now we shall discuss testing or classification procedure in detail. As we mentioned previously, the first sub-step of testing is called indexing. In this step, input samples are indexed into the KD3 in a parallel fashion. Here, parallel means that indexing considers all the samples from each example sequence and class at the same time, ignoring any class and timing constraint. Then, the nearest neighbors of each input sample from the training sequences are retrieved with respect to Euclidean distance function. Finally, similarity scores are assigned depending inversely on these distances. Here is a graphical representation of indexing procedure. As we can see, retrieved training samples and their corresponding distances are stored inside the cells of a matrix structure. On the horizontal axis, we have input samples, and on the vertical axis, we have different class or words which we want to recognize. Here we want to discuss sequencing, which is a basic part of our approach. Optimization and sequencing are very similar to optimal weighted bipartite graph matching, but with an additional temporal ordering constraint that must be followed. The sequencing is simply a requirement to keep the timing order in the links. It means that an earlier and a later samples in the input sequence cannot be linked with the later and earlier samples in the exemplar, respectively, and vice versa. For example, in the above diagram, links with 0.8 and 0.7 cannot be combined in the total summation, as they break the sequencing constraint even though they give a total high similarity measure. Our sequencing algorithm must take the links with 0.8 and 0.5, as they maintain the temporal sequencing order and have the highest total sum. Here we want to discuss a simple example of sequencing and dynamic programming. Input samples are denoted by T, and training samples are denoted by N. Now, in the diagram, input sample T3 has similarity measures of 0.3 and 0.9 respectively, with training samples N1 and N13. So initially, the link with training sample N13 is chosen as it has higher similarity measure compared to training sample N1. Now we have our second input sample, T8, which has 0.2 and 0.1 similarity measures with training sample N4 and N10 respectively. These two links give the total similarity measure of 0.5 and 0.4, considering the prior link of 0.3 similarity measure. However, both links are disregarded in this case, as the total similarity measures are lower than the previously chosen link, which has the measurement of 0.9. Here we have our third input sample, T13, which has 0.3 and 0.2 similarity measures with training samples N7 and N16 respectively. The link with 0.3 similarity measure is disregarded here, as it violates the sequencing principle. More specifically, training sample N7 comes prior to training sample N13, and the sample N13 is already chosen to be linked with training sample T3, which comes prior to training sample T13. So, by maintaining our sequencing principle, we have to choose the link with 0.2 similarity measure, even though it is lower than the similarity measure of 0.3. The total score now is 1.1, which is nothing but the direct sum of 0.9 and 0.2. Now we have our fourth input sample, T18, which has only one similarity measure of 0.5 with training sample N25. This link also follows our sequencing criterion, which means training sample N25 only comes after the previously chosen training samples N13 and N16. At this point, we get our total current score of 1.6 by simply adding 0.5 to the previous total of score of 1.1. Finally, we have our last input sample, T23. This sample has two similarity measures of 0.4 and 0.2 with training samples N19 and N28 respectively. However, the link with N19 cannot be chosen as it comes earlier to the training sample N25, which was chosen previously with input sample T18. So, we chose the link with N28, and this gives our final total score of 1.8, which we get by adding 0.2 to the previous total score of 1.6. The red arrows in the diagram indicate the finally chosen links, which represent the similarity among input and training samples. And here ends our detailed discussion on risk methodology. In Appendix 2, we shall discuss dynamic time warping, or DTW, which was used for speech recognition in the past. We describe it because it is superficially similar to risk. However, we shall show that risk is very different both in approach and in algorithms. First of all, DTW is a non-parametric method, which means that it does not need to establish parameters for the recognition. Secondly, DTW performs elastic matching to speech with speed variations, and that's an advantage. In DTW, the matching is done by minimizing distance between input and stored models. Here is just a sample graphical representation of DTW. Exemplar sequence, or sequence A, in this case, is placed on the horizontal axis, and input sequence, or sequence B, is placed on the vertical axis. The red dots represent the minimum cost path found after applying the complete DTW algorithm. Now we would like to get into brief details about the methodology of DTW. A local cost matrix is built to perform distance comparison. To understand this better, let's consider two sequences. Sequence X is the exemplar sequence, and sequence Y is the input sequence. We just put samples of both sequences in the horizontal and the vertical axis respectively. The local cost matrix is simply found by calculating the corresponding Euclidean distance between samples. Each element of the local cost matrix corresponds to the distance between a samples of X that corresponds to the column and a sample of Y that corresponds to the row. A global cost matrix is then built by accumulating values from the local cost matrix under certain constraints, such as the requirement for a monotonic path. It means the requirement not to go back in time. Finally, a minimum cost path is found by dynamic programming algorithm. In the diagram, you can see the global cost matrix and the corresponding minimum cost path, which is shown in red arrows. Although DTW is very easy to implement and analyze, it is not free of several shortcomings. First of all, a continuous path must be built for matching. This constraint makes DTW very difficult to implement for speech signal with several interruptions and pauses. Also, any interruption must be included in the path because the path must be continuous. So, if we have an interruption, we must include in the path at least one element with a large distance due to its dissimilarity to the real speech. This element could be dominant and change significantly the total distance of the path. Another problem with DTW is that we have to know the exact location of the starting and ending point of each sequence. This is a major problem because when we deal with continuous speech, there are no pauses between words, and therefore it is very difficult to find the locations of startings and endings. Finally, and most importantly, in a sequence of distances, one high-valued distance can determine the total distance sum regardless of other distances in the sequence. This shortcoming of DTW is very important to consider because a random mismatch in a sequence can throw an actual lowest cost path out of consideration, which could lead to an error. In comparison, our RISC doesn't have the shortcomings of DTW. Firstly, unlike DTW, we don't need to build a continuous path, even though RISC is also an elastic matching method itself. Secondly, we also don't need the information of starting and ending point, which can be very difficult to retrieve in case of continuous data sequence like speech. Finally, we are using similarity measure instead of distance measure. It is very important because in similarity measure optimization, the sequence doesn't have to be continuous, and the total measure is not affected by occasional dissimilarities. In Appendix 3, we shall discuss hidden Markov models, or HMM, which is the state-of-the-art and the most popular speech recognition method nowadays. HMM is a parametric method which is based on maximum likelihood approach. Here we are showing a sample hidden Markov model with 3 hidden states. Hidden Markov models are built up of a set of hidden states. These hidden states can be inferred only through observation of the emissions. In the diagram, omega 1, omega 2, and omega 3 are hidden states. Transitions between these states are random, but are influenced by the transition probability between the hidden states, Aij, in the drawings. Each hidden state of a hidden Markov model emits certain visible emissions. The probabilities of visible emissions are denoted by Bij in the diagram. In the diagram, V1, V2, V3, and V4 are the possible visible emissions from the hidden states, and the values on the visible emissions arrows correspond to the emission probabilities Bij. The classification process in HMM is inherently sequential and is performed on one model at a time. For each model, one has to compute the total probability of emitting the whole sequence. The total process is thus quite slow. With HMM, the entire sequence is needed to be processed. There is no way to skip some portion of a long sequence in the classification process. In the next few slides, we shall discuss a simple example of HMM classification procedure. At first, let's consider a model for a particular word where the hidden states are omega 1, omega 2, and omega 3. The visible emissions are V1, V2, V3, and V4. These visible emissions actually represent phonemes in that particular word. This is a sample hidden Markov model for a word that we want to recognize in speech. Hidden states, transition probabilities from one state to another, visible emission and emission probabilities are shown with arrows in the diagram. There can be multiple models for a word, and all the models with all their parameters are stored in a training stage. For a particular word, let's consider the sequence of phonemes, which is V2, V1, V4, V1, V3, and V4. These 6 phonemes come sequentially at 6 particular time instances during utterance. So we have t equals to 1, 2, 3, up to 6. A trellis diagram is a graphical representation of all the states at all time instances. Practically, the trellis could describe by a particular pass the states of the model at each instant. Actually, many paths are possible. For the recognition task, one has to compute the total probability of all feasible paths from t equals to 1 until equals to 6, while emitting the sequence V2, V1, V4, V1, V3, V4. The total probability of each model is computed, and the word sequence is classified as the model with the highest probability to emit it. To summarize, an input sequence is thus checked with all feasible models. Finally, the model with the maximum final emission probability is decided as the class of the input sequence. Here we are showing a recursive formula which is applied to compute the probability of a particular emission at a particular hidden state at a particular time. Despite being widely used state-of-the-art speech recognition method, hidden Markov models do have several shortcomings. First, a large number of parameters are needed to be estimated for each model. This requires a lot of exemplar data and many iterations of expectation maximization algorithm. This makes HMM very difficult to train and to adapt to different speakers. In many instances, training is impossible due to lack of enough exemplars. In contrast, RISC is very easy to train and does not need many exemplars. Actually, in many cases, just one exemplar is sufficient. RISC can be trained for any utterance in any language without the need to dissect words into phonemes and to train for each phoneme combination another hidden Markov model. In comparison, our RISC doesn't have these shortcomings of HMM. Firstly, unlike HMM, our approach is non-parametric. As a result, the implementation is way too simpler, and we don't need to train and handle large number of parameters. Secondly, only few examples are needed for the training procedure. Training is done by simply storing the training data into a multidimensional data structure. Finally, our classification procedure is partially parallel and therefore much faster than HMM, as this parallelism facilitates the checking of multiple words at once. So this was our discussion on HMM, and we would also end our presentation here.